Okay, so let's do the going up theorem. Going up. Okay, so roughly what this says is that that chains of prime ideals lift. So if A is contained in B is integral, then chains of primes lift two chains of primes. Uniquely, something like this. Okay. Let me explain this more precisely. So let me say this is around. So this is let me give kind of like a let me do this lemma first because it's kind of indicative of what's going on. So lemma. So let A subset of B be integral. So we have an integral extension of rings, and so if A is a field, then B is a field. Okay, and the proof of this is kind of an explicit computation. Okay, so let's do the proof. Okay, the proof says so if B, so we're going to just show that B has an inverse. If B and B satisfies some polynomial, so we can write it down. So A0 plus A1 B plus blah 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 plus AN minus 1 B to the N minus 1 plus B to the N is equal to 0. Then what can we do for the inverse of B, right? So what we'll do here is that we'll divide by, okay, so here's what we'll do. So this implies that A0 is equal to, okay, minus A1B plus blah 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 plus AN minus 1 B to the N minus 1 plus B to the N. Okay, now we can divide by A0, so we get 1 and then we can factor out by B. Okay, so we have B times, and then we have this thing minus A1 plus, okay, and then let's do this, A2, okay, I'll do that, A2B plus blah 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 plus AN minus 1 BN minus 2 plus BN minus 1. Okay, now we divide by A0, because A0 is a field, so we can do that. And then we find an explicit formula for the inverse, and this is an element of B. Okay, and so this proves that that every B has a multiplicative inverse, which is enough to show that it's a field. Okay, so this is one of the things that we have. Okay, and a consequence of this is the following. So let's do the following lemma. So lemma. Okay, and it says that if Q is a prime of B and P is a prime of A, with Q intersect A is equal to P. So this is a prime above, lying above P. So we say that P is below Q, or we say that Q is above P. Okay, and then let's say that A over B is integral. So this is so that the integral closure of A and B is just B. Then if P is maximal, so if the smaller one is maximal, then Q is maximal. Okay, so let's do the proof of this. So the proof is just an application of this the lemma that we had about quotients. So we had the state properties about integral closures, and one was like the tower property, one was about localization, one of them was about quotients. Okay, So since a over b is integral, or sorry, since b over a is integral, so the map here, a mod p to b mod q. So you can really just map a to b mod q, and then look at the kernel of this. The kernel of this is q intersect a, which is p. Okay, so this is really a subring here. But we can do integral closures with respect to maps, and that's not really a big deal. So then the map is integral. Okay, so this is an integral extension. Okay, since p is maximal, a mod p is a field, and hence and so okay, let's do that. And so this proves that so by the previous lemma, b mod q is a field, and q is maximal. All right, that's all we have to say about that. Okay. All right. Okay, so that's kind of a cool thing. So it says that if you look at the inverse image of a point, closed point, or if you have something whose image is a closed point, then it'll be closed itself in this integral extension. Okay, so all right. So let me do theorem, and this is the going up theorem. Okay. So so it's about integral extensions. Be an integral ring extension. Okay. So if so Q1 and Q2 are in spec B with Q1 intersect A, so they're 2 primes above B. And this is equal to Q2 intersect A, which is P, okay? And let's say Q1 is contained in Q2, then Q1 is equal to Q2. Okay, so it's possible for there to be multiple primes above a given prime, but if their intersection is non-zero, right? Or not that their intersection is non-zero, but if one is contained in the other, then they're going to be equal. Okay, so let's do that. Okay, so let's prove this. So this is a statement that I said about chains of primes, is like you, yeah. So these things will, you don't get to have this sort of inclusion while this is holding at the same time. Okay, so let's do a proof. Okay, so. Okay, so if okay, let's do this. So okay, so if P is maximal, right? Then by the lemma, so is Q1, and hence Q1 is equal to Q2 by maximality. Okay, so then, okay, so this is the maximal case. If it's not maximal, well, we'll make it maximal. we make it maximal by localizing. Okay, and what do I mean by this? So we know that since this is integral. This implies that if we localized at p, both things at p, this is also integral. Okay, and we also have that localization respects intersections. So we also have that S inverse of Q1 intersect AP is equal to SP inverse. Then we have SP inverse Q2 intersect AP. So this is PAP, which is, maybe we can call this PP. Okay, so this is also the maximal ideal at the localization of the prime ideal P. Okay. All right. So this shows. So by this maximality assumption. So we have that SQ inverse, this thing here, is equal to SP inverse of Q2. Okay, in spec BP. Okay, but so we have equality of these two prime ideals in here. Okay, but we know that spec BP here, right? This is contained in here, B, and it respects the. So this can be identified as a subset. So we will write it as a subset, like we said before, right? So and so with where SP inverse of QI identifies with QI, right? And so this shows that that Q1 is equal to Q2, because it's true in the localization, and these things are the same thing as, this is an injective map of topological spaces containing Q1 and Q2, right? And they're equal here, so they must be equal in there, which means that the two prime ideals must be equal. All right, and that's that. Okay. So cool. Yeah. Maybe I can say something about this. That Q. Another thing to check is, when do these ideals become trivial? Well, the ideals become trivial exactly when the multiplicative set you're localizing at and the ideal Q have a non-empty intersection. Then that becomes silly. And the way that these make sense. So this thing here is in correspondence with the set of prime ideals of Q, such that the intersection of the prime ideal with the multiplicatively closed set that you're localizing, namely the complement of A with the prime ideal P, is empty. Okay, so the prime ideal is really contained in Q. So yeah. Okay, that's the going up theorem.